Is the AI revolution we are currently living through actually a structural regression to the computing model of the 1960s?
That is a fascinatingly provocative way to frame it. I mean, it's the single most important technology story of our time, right?
Right.
We associate AI with the absolute peak of futuristic progress. Trillion-dollar valuations, generative models creating entire worlds out of thin air. The default mindset is that this is all completely unprecedented.
And that default assumption is exactly what we need to challenge today. What if we're mistaking let's say, the speed of the change for genuine architectural innovation? Because when you really look at how this infrastructure is being built, how it's being funded, it looks less like a leap forward and more like a return.
You see this comparison all the time in the media, don't you? Analysts look at the market hysteria, the rapid influx of capital, the dizzying valuations, and they immediately jump to the dot-com bubble of 99, 2000.
They say, here we go again. It's all hype.
But if you look beneath the stock price, if you really examine the physical and the economic architecture, that comparison it fundamentally misses the mark.
Completely. The dot-com era was defined by decentralization. It was all about the explosion of the cheap, distributed client-server model, the rise of the PC, the internet making computing ubiquitous and abundant. It was a structural shift outward to the edge.
And that's the conceptual pivot we need to make. The history of computing is usually taught as this relentless, linear march of progress,
From the clunky, room-sized mainframe
to the personal computer, to the laptop, and now to the incredibly powerful device that's sitting right in your pocket. But what if the sheer overwhelming scale and specialization that modern AI requires is forcing that pendulum back to the center?
We're talking about these massive centralized AI clouds designed around specialized hardware clusters that are worth tens of billions of dollars. This isn't decentralized abundance, it's centralized scarcity.
So that's the core question for today.
Is this a structural throwback? Is the entire infrastructure running on thousands upon thousands of Nvidia GPUs Is it just the modern iteration of the 1960s glasshouse?
The physical structure has changed, for sure. It's moved from being this transparent, showy corporate symbol to, an opaque, hidden industrial plant. But the economic and the architectural structures, the centralization, the specialized priesthood, the capital expenditure, they have recurred with just stunning precision.
I'm Satoshi.
And I'm Satoshi.
Okay, let's unpack this. The source material that really anchored this deep dive for us was a truly exceptional piece of work. It's a paper titled The Cathedral and the Cloud, a comparative structural analysis of enterprise computing cycles, 1960-1990, and the artificial intelligence infrastructure boom.
And that paper gives us the core metaphor for our entire discussion today, the oscillation between the cathedral and the bazaar.
The cathedral representing what exactly?
The cathedral is centralized power. It's top-down control, massive capital intensity, proprietary systems. It is the absolute epitome of the early mainframe era.
And the bazaar is the opposite.
The bazaar is the chaotic, horizontal, open model. It's the decentralized ecosystem built on open standards, low entry costs, and massive participation. It's what defined the personal computing revolution. The paper argues, and I think we agree, that the industry is swinging away from the decentralized bazaar model of the PC and smartphone and oscillating violently back toward a centralized, capital-intensive cathedral model.
And that structural shift is what makes the AI revolution so architecturally distinct from the dot-com boom.
It has profound implications for anyone trying to figure out where the real value and, the real risk actually lies.
So today we're going to trace these parallels across 4 distinct areas. We'll start with the physical architecture, the new glass house, and the thermal constraints that are frankly defining it.
Then we'll get into the human dimension. We'll look at the culture of high-latency computing and the return of the technical priesthood who manage these incredibly scarce resources.
And third, we'll dive into the economic battles. We'll contrast the vertical integration failure of Route 128 with today's closed AI labs, and we'll look at the cautionary tale of specialized hardware, like the Lust machine.
And finally, we'll look at the socioeconomic parallels, comparing the infamous Nifty 50 stock bubble to today's Magnificent Seven, and showing how the automation anxiety of 1964 is a It's a beat-for-beat reprise of today's AGI fears.
It's a journey into the recurring patterns of technology, suggesting that sometimes the most revolutionary technologies just recast the oldest dramas.
Indeed. Understanding these cycles is really the shortcut to understanding the structure of the next decade of innovation.
Before we jump into all that, I just want to pause and welcome you all again and just say thank you for the amazing response to the show. We're seeing so much engagement on every platform, and it's clear you're all as fascinated by these deep dives as we are.
We really do appreciate the support.
And to keep producing this content, and importantly, to start creating some high-quality companion videos for YouTube that can help visually explain some of these really dense concepts, we need your help.
Yeah, we're trying to unlock funding for a new video editing tool, Mosaic AI Video Editor, and the key to that is hitting a benchmark of 1,000 subscribers across all podcasting platforms.
So please, if you enjoy these discussions and you want to see us elevate the content with visual explainers, take a moment right now and subscribe on YouTube, YouTube Music, Spotify, Apple Podcasts, or wherever you happen to listen or watch. Every single subscription helps us fund the next deep dive.
Okay, let's jump back in.
Let's do it. So, this story of enterprise computing, it isn't a straight line. It's a pendulum, swinging between centralization and decentralization. The story of the original Cathedral really starts with a colossal gamble, IBM System 360. This wasn't just a new product. It was an inflection point that basically dictated the structure of enterprise computing for decades to come.
Right. The System 360, announced in the spring of '64, that was the moment the enterprise platform was truly codified. Before it, computing was just chaotic.
How so?
Well, if an IBM customer had, say, a small 1401 machine for printing payroll, and they wanted to upgrade to a powerful 7090 mainframe for scientific calculations, they were stuck. They had to rewrite all of their software from scratch.
That friction sounds nearly insurmountable for a growing company. It just locks you into whatever hardware you started with.
Exactly. And IBM realized that the key to unlocking the entire enterprise market was to offer a migration path, a way to unify their entire diverse product line. This required a huge investment. The System 360 project was estimated to be a $5 billion investment.
$5 billion.
And to put that in context, that was roughly double IBM's annual revenue at the time.
Tom Watson Jr., IBM's president, famously called it the biggest, riskiest decision I ever made. What made the S360 so revolutionary that it justified that kind of bet the company risk?
The revolutionary concept was the Unified Instruction Set Architecture, or ISA. By creating a single, consistent ISA, IBM fundamentally separated the software from the hardware. Which means the same executable program could run seamlessly across a vast range of machines, from a relatively low-cost entry-level system to a massive multi-million-dollar mainframe.
The ISA was the foundation of the platform.
Yeah.
It let IBM basically consolidate all these formerly distinct domains, scientific, commercial, data processing, into a single technological, a hegemony.
It invented the platform business model in computing. It created these massive network effects for software developers who only had to write their application once to reach the entire spectrum of IBM customers.
Okay, so if that unified ISA was the codifying platform of the 1960s Cathedral, what's the modern equivalent? We don't really talk about low-level ISAs in the AI world in quite the same way.
The unifying layer has shifted. It's moved upward from the instruction set architecture to the software-hardware interface. And that interface is unequivocally NVIDIA's CUDA stack. Just as the S360 unified data processing across all these different scales of IBM machines, CUDA unifies inference and training across scalable clusters of GPUs. It doesn't matter if you're using a single chip on a developer's desk or a massive HGX supercomputer cluster spanning 100 racks. It's all CUDA.
And the risk profile of investing in this modern platform, it mirrors the 1960s, just on a much, much larger nominal scale.
The financial magnitude is identical in relative terms. IBM's $5 billion gamble was twice its annual revenue. Today, the hyperscalers, Google, AWS, Microsoft, they're investing tens of billions of dollars annually in GPU clusters.
Yeah, it's not optional.
These investments are mandatory. To offer competitive AI services, they have to commit capital on a scale that is a significant fraction of their total infrastructure budget. It's the same bet the company dynamic.
I have to push back a little on the direct comparison, though. I mean, the original S360 was a single vendor's IBM's centralized proprietary system, dominating a single physical site. Isn't the modern AI cloud, despite its massive capital demands, still fundamentally different because it's a distributed, globally redundant, pay-as-you-go utility?
That's a really important distinction to raise, and it highlights where technology has progressed. The delivery model is obviously superior. We have elasticity and global scale, but the architectural structure remains centralized.
Because?
Because the core resource, the H100 GPU cluster, is simply too capital intensive to be replicated at the edge. Even if you're accessing it through a browser, you are still renting time on a scarce, vertically integrated, multi-billion-dollar machine located hundreds or thousands of miles away. The economic barrier to owning that computational capacity is what defines the architecture as centralized, regardless of the cloud wrapper.
That makes perfect sense. The centralization is driven by cost and scarcity, and the scarcity is, in part, driven by fundamental physics. We have to talk about the thermodynamics of intelligence.
This is where the physical return of the glasshouse becomes just undeniable. The physical data center of the 1960s was massive and often built with literal glass walls.
They weren't just for show, right?
They weren't just aesthetic, they served a purpose. They were spectacles of conspicuous consumption designed to project corporate status, balanced against the need for this hermetic, temperature-controlled environment to ensure the machine was stable.
And the heat challenge of those early mainframes was the defining constraint.
Absolutely. As mainframes grew in power in the 70s and 80s, simple air cooling, it began to fail completely. If you look at the IBM 3081 and 3090 systems of the 1980s, they were wrestling with massive thermal loads far exceeding what air could handle efficiently.
And that's where we get this fascinating technology, the thermal conduction modules, or TCMs.
TCMs were IBM's incredibly sophisticated answer to thermal management. There were these complex, water-cooled devices that contained helium-filled pistons used to draw heat away from the dense processor chips.
Just to give a sense of scale.
For the S360 era, the heat flux was around 0.3 watts per square centimeter. By the time you get to the 3090s, the heat flux had risen tenfold to about 3.7 watts per square centimeter.
Why did they use helium specifically? Why not just air or water in the module itself?
The choice of helium was critical. It's a non-reactive, inert gas with very high thermal conductivity, much, much higher than air. So using a sealed, helium-filled chamber provided a really efficient insulating medium to transfer heat from the silicon surface to the cold plate, which was then actively cooled by a closed-loop water system.
The sheer complexity of that, using helium and chilled water, it shows just how desperate they were to manage those rising heat levels while keeping the machine running.
And if we look at the modern AI cluster, we're facing that exact same problem, but scaled up by a magnitude that just makes the 1980s look quaint.
The parallel is exact, but the physics are brutal.
Modern AI chips like the Nvidia H100 are facing heat fluxes that exceed 100 watts per square centimeter. This exponential increase means air cooling is completely obsolete for high-density train clusters.
So the transition from air-cooled S360 to water-cooled 3090s in the 70s and 80s is being precisely mirrored today by the shift from air-cooled server racks to liquid-cooled H100 racks.
It's a precise architectural echo, and it's driven by the exact same fundamental thermodynamic limit. Today, data center operators are rapidly moving to liquid-cooled AI clusters using direct-to-chip liquid cooling systems.
It's incredible.
Just as 1980s IBM engineers became expert plumbers, wrestling with water quality, filtration, pressure, flow rates. Modern data center architects are now redesigning entire facilities for hydraulic requirements: tanks, pumps, manifolds, leak detection systems.
The complexity has returned, but the visible manifestation is gone.
The glasshouse has returned, but it is now opaque and hidden. It's a massive, environmentally controlled black box buried in remote hyperscale data centers in places like rural Virginia or Iceland. But its function is the same: to house and cool the intensely powerful, centralized engine of corporate intelligence, completely inaccessible to the masses.
The centralization of the machine wasn't just about cooling. It dictated the whole culture, the whole hierarchy. And this brings us to the human factor. The rise of the specialized priesthood who control access to that scarce resource.
To really appreciate the power of that priesthood, we have to first immerse ourselves in the sensory environment of a 1960s data center. It was a space that demanded respect and a very, very specific type of expertise.
So paint the picture. What did it feel like to be near that computing power?
It was an assault on the senses. The air had this distinct, sharp, almost metallic smell. Ozone, exactly, generated by the high-voltage electronics and the massive constant output of the line printers. And you'd often smell stale cigarette smoke mixed in because operators who lived in that environment were frequently allowed to smoke at the console, a concept that's just unimaginable in a server room today.
And the sound, I imagine it was deafening.
Oh, it was deafening. You had the constant low roar of the massive air conditioning units essential for thermal stability, competing with the rhythmic mechanical clatter of the line printers churning out fanfold paper. And most evocative of all was the loud, characteristic whoosh of the vacuum column tape drives as they spooled and unspooled data. That was the sound that signaled the machine was actively working.
And the tactile experience of programming itself was heavy. It wasn't abstract code on a screen.
No, it was profoundly physical. Programmers carried their logic in decks of 80-column punch cards. A typical program deck, maybe 2,000 cards, weighed around 10 pounds.
And if you dropped it,
If you dropped a deck, it was catastrophic. You would spend hours manually resorting those cards, sometimes relying on sequencing numbers punched in the corner columns just to get your program back in order.
that mental image alone explains why the operational mode of the era batch processing was so culturally defining.
Batch processing enforced this high-latency feedback loop, which completely defined the culture. The process was a strict, high-stakes ritual. You'd write your code on coding sheets, which were then handed to key punch operators who transcribed them into the actual punch cards.
And then came the moment of submission to the gatekeeper.
The programmer, the supplicant, would submit their deck through a small window to the computer operator. This operator was the ultimate gatekeeper, often wearing a white lab coat, which symbolized technical specialization and, more importantly, control over the machine. The machine was seen as the corporation's scarce, vital asset.
The job enters a physical queue, and the programmer just walks away, knowing they won't see the result until, what, the next day, maybe even later?
Oh, turnaround times could easily exceed 24 hours. The output, a stack of green bar fanfold paper, would appear in a designated pigeonhole the next morning. If your card had a single mispunched comma, the entire run failed. The whole process had to be repeated.
That scarcity of compute time must have created a massive pressure for discipline.
It forced programmers into what they called desk checking or mental compiling. Before submitting the code, they would spend hours, literally hours, simulating the machine's logic in their heads, tracking register values and memory addresses with paper and pencil, just to ensure they weren't wasting a precious and costly run.
A culture of scarcity breeds precision, a stark contrast to the instant gratification and rapid iteration of modern software development.
And this is the core argument, that high-latency batch job is returning in the AI world, and with it, the cultural discipline and the priesthood.
How so?
It is the defining feature of modern large language model training. While simple inference, using ChatGPT is instantaneous, the creation of a foundational model is a massive, high-latency batch job that often runs continuously for weeks or even months. The scarcity has shifted from punch card decks to GPU hours, which cost millions.
And the cost of failure is astronomical, making that mental compiling relevant all over again.
Exactly. If a multi-week run fails because of a configuration bug, an infrastructure hiccup, or a loss curve divergence, millions of dollars in compute time and weeks of effort are just gone. The AI researcher setting up the run has to ensure their distributed training framework is flawless before they commit that scale of capital and time. It demands the same profound precision as desk checking.
So we have a new priesthood running the new cathedral. Who holds the white coat now?
Well, the AI researcher designing the algorithms is the new supplicant programmer. But the DevOps MLOps engineers, the specialized staff managing the temperamental multi-billion-dollar GPU clusters, they are the new white-coated operators. They are the true gatekeepers of the new machine.
And how does their role today mirror the 1960s operator?
The MLOps engineer manages the resource allocation, the scheduling, the data flow, and, critically, the physical maintenance, including those liquid cooling systems we just talked about. They control the queue for access to the scarce GPUs. They possess this specialized knowledge that goes way beyond standard software engineering. It's the dark art of distributed, power-dense, multi-node compute infrastructure.
Their expertise is required to keep the intelligence factory operational,
which creates a clear hierarchical separation between the user, the researcher, and the controller, the operator. The architecture has successfully rebuilt the culture and the hierarchy of scarcity.
But the mainframe cathedral, with its capital cost and its operational priesthood, it inevitably provoked a massive counter-reaction. This was the mini-computer rebellion, a push toward decentralization that ushered in the bizarre model.
This rebellion really started in earnest in the 1970s. It was pioneered by companies like Digital Equipment Corporation, DEC, with machines like the PDP-8 and the immensely successful VAX 01780.
And the key was scale and cost.
The key was scale and cost. These machines were cheap enough, relatively speaking, and small enough for individual departments, a university physics lab, an engineering team, a small company, to own and operate them without relying on the central corporate computing monopoly.
This wasn't just a hardware change. It fundamentally altered the relationship between the user and the computer.
It was a profound cultural shift. The VX facilitated interactivity through time sharing and terminals, completely eliminating that punitive, high-latency batch processing culture. The feedback loop shrank from days to seconds. This gave rise to the concept of the sovereign user, the person with direct, often root-level access, who is in direct control of their own computing power.
The VX became so central to this cultural and technical shift that it gave us an early universal unit of measurement for performance.
Indeed. The VIX 1180 became the industry standard for benchmarking, giving us the VX unit of performance, or VUP. Every new computer was rated by how many VUPs it could deliver.
So it's like an early precursor to our modern obsession with FLOPs and parameter counts.
A direct ancestor. The VUP was an essential tool for the bazaar, allowing the nascent, decentralized market to compare competing hardware accurately.
That movement really climaxed in the workstation era, defined by companies like Sun Microsystems, who basically placed the power of a fax right on the user's desk with machines like the SparkStation. That truly empowered the user.
And this movement played out on a very clear geographic stage, which offers a crucial historical parallel for today's AI industry. The rivalry between Route 128 in Boston and Silicon Valley in California. This competition shows us the dangers of vertical integration.
Okay, let's contrast these two models because the failure mode of Route 128 is so relevant to today's closed AI labs.
The Route 128 model, exemplified by companies like DEC and Wang, was defined by rigid vertical integration. They built everything themselves.
Everything.
The custom chips, the proprietary operating system, which was VMS, the peripherals, the networking protocols like DMET. The culture was formal, hierarchical, risk-averse, and insular, the classic company man era. Sharing information outside the company was seen as a threat, not a benefit.
And Silicon Valley was the inverse. It was the model of the bazaar.
Absolutely. The Silicon Valley model, championed by Sun, HP, and others, was defined by horizontal integration and open standards. They adopted standard Unix, usually BSD, standard networking, Ethernet TCP/IP, and standard commodity microprocessors. Their culture was networked, fostering high labor mobility and cross-pollination of ideas. Failure was tolerated as part of rapid learning.
Which allowed Sun to coin their prophetic slogan.
The network is the computer.
So why did the insularity of Route 128 prove fatal in the long run?
They failed because they delayed the shift to open standards. DEC was too protective of VMS, its proprietary OS, and DSNet, its proprietary networking. They dragged their feet on adopting Ethernet and TCP/IP because they believed their vertically integrated proprietary solutions were technically superior.
Which they might have been in isolation.
But it allowed the West Coast firms, which embraced the standard horizontal and modular architecture, to commoditize the underlying hardware and accelerate innovation at the software layer. Ultimately, they crushed the Route 128 firms in the market. The Cathedral was dismantled by the collective power of the bazaar's openness.
So what does this tell us about the current AI landscape, this split between the closed and the open models?
It suggests that history is rhyming with precision. You have the closed labs, OpenAI, Google DeepMind, Anthropic maintaining proprietary weights and architectures, trying to own the full AI stack. They are the new Route 128 vertical integrators.
And the open ecosystem.
That's the bazaar. It's Meta's Llama, it's Mistral, it's the massive collaborative ecosystem of Hugging Face. History suggests that while the closed integrators may dominate early revenue due to proprietary performance advantages, the horizontal open model eventually commoditizes the stack and drives broader, faster innovation.
Potentially undermining the Cathedral's proprietary advantage in the long run.
The lessons of the 1980s are a stark warning for today's closed AI giants.
That tension between specialization and commoditization is so critical, and we see it playing out in the hardware cycle too. Before we get to the dominance of Nvidia, we have to look back at the original specialized AI hardware, the cautionary tale of the Lisp machine.
Oh, the Lisp machine story is mandatory listening for anyone investing in custom AI hardware today. In the 1980s, AI was basically synonymous with the Lisp programming language, and companies like Symbolics and Lisp Machines, Inc. designed specialized hardware tailored specifically for it.
What made them so specialized, and why was this even required for Lisp?
Lisp had these unique requirements, primarily intensive garbage collection and highly dynamic typing. The Lisp machines use these exotic, non-standard 36-bit tagged architectures explicitly optimized to handle these features in hardware. They were, technically speaking, far superior machines for running complex Lisp AI code compared to the general-purpose CPUs of the time.
They were the original high-performance specialized AI chips.
But their technical superiority didn't translate into market victory. They were economically doomed. The killer micro. The rapidly advancing standard CPUs from Intel, Motorola, and Sun, they advanced so quickly, funded by the volume economics of the PC market, that they could eventually emulate Lisp in software faster and cheaper than Symbolics could build specialized custom hardware.
So the specialized, technically superior AI chip was crushed by the sheer economic power and pace of the general-purpose chip industry.
And this history, then, poses a clear existential threat to the current wave of specialized AI inference chips, the ASICs and LPUs being designed today.
We have seen this movie before.
We have. If general-purpose GPUs, backed by the trillion-dollar gaming and data center markets, continue to improve this rapidly, then hyper-specialized AI hardware, which lacks that massive volume funding, risks the same extinction event as the Lisp machine. The economics of volume are relentless. They often beat technical niche excellence.
Which brings us to Nvidia, the company that somehow threaded this specialization commoditization needle perfectly. They made a truly prophetic bet way back in 2006.
The bet was CUDA. Nvidia transformed the GPU from a niche graphics engine into a general-purpose parallel supercomputer on a chip. And this wasn't a cheap pivot. It required a sustained investment of over $1 billion before deep learning even became mainstream.
And as you mentioned earlier, the brilliance of CUDA wasn't just the hardware itself, but the software bridge that standardized access to it.
Precisely. CUDA provided a unified software layer that allowed developers to use familiar C, C++i, and Fortran extensions for parallel programming. Before CUDA, accessing the GPU's immense parallel power required this arcane knowledge of graphics APIs, which limited its use to a handful of specialists. CUDA democratized parallel computing for the entire research community.
And the ultimate proof of concept for this massive investment came in 2012 with AlexNet.
AlexNet was the big bang moment for modern deep learning. At the ImageNet Challenge, the model achieved a 15.3% error rate, which just shocked the computer vision community by dramatically outperforming the runner-up. The sheer scale and speed of this achievement proved that deep learning was finally viable.
And it was only feasible on Nvidia hardware.
Yes. The training was done using two high-end consumer GPUs, the GeForce GTX 580s. The process took about 5 to 6 days. If they had attempted that same computation on the top-of-the-line CPUs of the era, it would have taken months.
So AlexNet validated Nvidia's entire decade-long thesis.
And the power of this synergy lies in the core mathematics of AI matrix multiplication, which is inherently parallel, a perfect match for the GPU architecture.
And Nvidia was strategically brilliant in responding to this validation.
They doubled down on specialization within the general-purpose GPU. They introduced tensor cores in the Volta architecture in 2017. These were specialized processing units explicitly designed to accelerate the mixed precision matrix math that is the core operational engine of deep learning.
They also had to solve the data bottleneck. A GPU with thousands of cores is useless if it's starving for data.
Right. So Nvidia invested heavily in specialized high-speed memory, the high bandwidth memory, HBM, which provides staggering data bandwidths up to 155 gigabytes per second, ensuring that the cores are constantly fed the data they need for training.
So if the hardware opened the door, the software built the fortress. This is the trillion-dollar moat that locks developers into the ecosystem.
The moat is the years and years of accumulated engineering in the CUDA X AI software stack. It's a vast collection of specialized libraries that are essential for large-scale production. We absolutely must talk about NCCL specifically.
NCCL. What does it do that makes it so sticky?
NCCL stands for the NVIDIA Collective Communications Library. Functionally, it's the choreography layer. When you're training a massive LLM, you're not using one GPU. You're using hundreds or thousands across multiple server nodes. NCCL provides the highly optimized routines necessary for those GPUs to communicate, to synchronize gradients, and to share data efficiently with very, very low latency.
So if a developer wants to scale their training run to, say, 1,000 GPUs, they are fundamentally relying on NVIDIA's software stack to manage that complex synchronized communication.
Precisely. Rebuilding that optimized, low-latency communication layer is almost impossible for an individual competitor. NCCL, alongside other components like CUDA for optimized deep neural network primitives, And tensor idea for high-performance inference optimization creates massive developer lock-in. You simply cannot get the same scaling performance without using the Nvidia stack.
And Nvidia solidified this control by ensuring they control the entire system, not just the chip, transitioning into an AI factory provider with their integrated DGX and HGX systems. They even secured the last major bottleneck, networking.
The acquisition of Mellanox in 2019 was the strategic masterstroke that completed the vertical integration. At the massive scale of modern training clusters, the speed at which data moves between servers, the interconnect, is as crucial as the computation speed within the server. Mellanox gave them control over InfiniBand, the highest speed, lowest latency networking standard necessary to scale these clusters linearly and guarantee performance stability.
By controlling the GPU, the interconnect, and the full software stack, Nvidia has achieved near-total vertical integration in the AI data center. But the very scale of this success has created an inevitable counterreaction.
The customer has become the competitor.
This is the classic platform war dynamic.
Exactly. The hyperscalers, Google, AWS, Microsoft, are now spending billions designing their own custom chips. The TPU, Trainium, Inferentia, Maya, all designed specifically to reduce their costly dependence on Nvidia and optimize for their own internal proprietary workloads. They're the only companies with the capital and the volume to even attempt this. They're effectively trying to replicate the Cathedral architecture internally.
And this push confirms the Lisp machine lesson. The ASIC risk is real, especially for inference workloads.
Inference, which is the high-volume, repetitive task of running an already trained model, is the ideal target for specialization. As that workload standardizes, specialized ASICs from hyperscalers or partners like Broadcom become economically viable alternatives to the more flexible but more expensive general-purpose GPU. Nvidia is dominating the high-margin training market, but the inference market is ripe for commoditization by ASICs, repeating the fate of specialized chips from the 1980s.
Okay, now we move from the physical infrastructure and the hardware wars to the economics and the social psychology. Because the mainframe era didn't just give us the glass house, it gave us the nifty 50.
This financial parallel is genuinely striking. The market sentiment of the early 1970s was dominated by the Nifty 50. Institutional investors concentrated wealth into about 50 stocks, blue-chip growth companies like IBM, DEC, Xerox, and Polaroid.
They were viewed as one-decision stocks.
Right, companies so dominant they were deemed immune to economic cycles.
That sentiment sounds exactly like the narrative around today's Magnificent Seven.
It is the exact psychological pattern, and the valuations reflected this hysterical belief in inevitability. In 1972, the Nifty 50 stocks averaged a price-to-earnings ratio of 42x, which was more than double the average S&P 500. Polaroid, seen as the innovative tech titan of the moment, traded at a staggering 90 times earnings.
The core belief was, buy these and hold them forever because they own the future.
And the inevitable crash was brutal. The 1973-74 bear market completely decimated them. Xerox fell 71%, IBM fell 73%, and Polaroid dropped a terrifying 91%.
The lesson there isn't that technology fails.
Exactly. The lesson is that a company can be absolutely vital and technologically monopolistic like IBM was, and still be a disastrous investment if you bought it at the peak of market hysteria, where the price reflects decades of future growth already factored in. The Magnificent Seven is currently riding that same psychological wave of perceived inevitability.
And moving from the financial bubble to the social fear, we see another perfect reprise: automation anxiety. Today we talk about AGI replacing white-collar work, but the 1960s were dominated by fears of job elimination through cybernation.
The panic wasn't just in academic journals. It reached the highest levels of government. In 1964, a group of Nobel laureates and activists sent the famous Triple Revolution memo to President Lyndon B. Johnson.
And what was the core argument of that memo?
They warned that cybernation, the combination of automation and computing, would fundamentally break the link between income and employment. They argued that machines would create permanent structural unemployment, resulting in a large, marginalized underclass that could never be absorbed back into the workforce. The media widely warned of a jobless future where machines would replace not just physical labor, but mental and intellectual labor, too.
That is a beat-for-beat match for today's headlines about AI eliminating knowledge work.
It's an exact psychological echo. But the historical outcome provides the counterpoint to the panic. Unemployment actually remained low throughout the 1960s and 70s. The technology didn't eliminate labor entirely. It shifted it dramatically. primarily from manufacturing and blue-collar jobs into the burgeoning service and white-collar sectors.
So the fear was real, but the predicted outcome was structurally flawed.
Correct. And today's AGI discourse, predicting the end of white-collar work and the rise of the permanent knowledge worker underclass, is a reprisal of the 1964 panic. We can anticipate that it will likely resolve in a similar transformation of work, a massive shift in what skills are valuable, rather than a cessation of work altogether.
That structural transformation leads perfectly to perhaps the most useful lesson about second-order effects, the paperless office paradox.
The classic technological misprediction. In 1975, a Business Week article predicted that office automation would eliminate paper entirely by 1990. And the logic seemed sound. If computers digitize documents and communication, we won't need physical paper anymore.
But the reality was the exact opposite.
The reality was that paper consumption doubled between 1980 and 2000. And why? Because computers and laser printers lowered the cost of generating a paper document to near zero. It became effortless to print, copy, and file multiple copies of everything.
When the cost of production drops, volume explodes.
It's an iron law of technology.
So applying that paradox to AI, if AI lowers the cost of generating code, music, articles, and content to near zero, we shouldn't expect fewer software developers or content creators. We should expect an explosion in the volume of content.
Exactly. The AI implication is that we will soon be drowning in auto-generated content and code. The critical bottleneck shifts entirely. It's no longer about production, it's about post-production. The value shifts to verification, curation, integration, and most importantly, human judgment and taste. The role of the AI integrator or AI curator, who can discern high quality from infinite low-cost output, will become immensely valuable.
Technology rarely subtracts work. It only changes its nature and shifts the necessary skills up the value chain. This entire deep dive brings us back to the core structural insight we started with. The AI boom represents a profound, decade-long reversal in the history of computing architecture.
It's the reversal of a 50-year trend. From the rise of the mini-computer in the mid-70s onward, computing power migrated from the centralized center, the mainframe, to the edge, to the PC, the smartphone. We experienced this golden age of decentralization and user sovereignty.
But now we are undeniably in a centralization supercycle.
The sheer capital intensity, the physical demands of thermodynamics, the specialized expertise required to train these massive LLMs, it's all caused computing power to collapse back into the center, the hyperscale AI cluster in the cloud.
The H100 GPU cluster is the new mainframe.
And structurally, it shares all the defining characteristics of the old Cathedral. Absolutely. It's too expensive for individuals to own a single unit, costs $25,000 or more, making it an industrial commodity. It resides in a remote, temperature-controlled, power-dense glass house managed by a specialized priesthood of MLOps engineers.
And users interact via simple API or browser terminals, having completely lost the sovereignty they enjoyed during the workstation and PC era. The machine is the master of the center once again.
The structural analysis provides a critical perspective on the current investment climate. It offers both a warning and maybe a stabilizing perspective.
Warning is clear from the Nifty 50.
We are in a massive CapEx supercycle where companies are spending billions on infrastructure and Nvidia chips, custom data centers driven largely by projected, not realized revenue. When this infrastructure build-out inevitably outpaces the immediate utility of the applications, a violent market correction is inevitable for the investors who bought at peak hype.
But if the history of computing is a story of cycle centralization, giving way to decentralization, only to swing back again, are we just destined to repeat these cycles forever? And what does this cycle imply for the infrastructure layer?
That is the essential, provocative question for the next decade. Historically, the open ecosystem of the bizarre Unix, TCP/IP commodity PCs, it eventually won against the cathedral of the vertically integrated mainframe. Will the same happen with AI? Or is the capital intensity required to train multi-trillion parameter LLMs, the physics of the H100 cluster? Is it simply too high this time around to ever allow true grassroots decentralization? Is the modern cathedral structurally unassailable in a way the old one was not?
It's the essential tension between open innovation and industrial scale. And one final stabilizing thought. If this AI cycle is fundamentally structural, like the massive enterprise machine build out of the 60s and 70s that required years of infrastructural investment before applications truly took off, then we can be confident that we are decades away from a true bubble, at least for the infrastructure builders themselves. The groundwork is only just being laid.
which means the CapEx cycle is likely long and deep.
The economic calm for the infrastructure builders, but volatility and churn for the application layer sitting on top. This has been an in-depth exploration based on extensive public analysis, and we want to remind you that this conversation is part of an ongoing deep dive. It is a community effort.
The analysis in this episode is based on publicly available information, but the story is still unfolding in real time. We invite you, our listeners, to share your own analysis and sources in the comments. Are we being too optimistic about the bazaar winning this time? Too critical of the structural staying power of the cathedral? We really want to hear your critiques and alternative interpretations.
We're always looking for collaborators to review our content. So if you're a finance expert, a deep learning practitioner, or even a crypto native with a sharp eye for detail and a knack for comparative analysis, please reach out to us. We'd love to have you review our materials as we continue to build out this framework.
Thank you for joining us on this deep dive into the history and architecture of the AI revolution.
Keep searching. Keep the quest on.